Welcome to my Artificial Intelligence through Artificial Intelligence YouTube channel and the Introduction to Deep Learning and PyTorch course. This is a continuation of Video 8, where we explored saturation, its challenges, causes, and solutions. In this session, we will focus on the vanishing gradient problem. To properly grasp the vanishing gradient problem, it's essential to understand these key concepts: loss functions, backpropagation, early versus later layers, gradients, derivatives, partial derivatives, and the chain rule in backpropagation. So, in this video and the following ones, we will explore these concepts before diving into the vanishing gradient problem. Let's begin with the loss function. It measures how well the neural network's predictions match the actual values. It highlights the difference between the predicted output and the true output. The goal of training is to minimize this loss. Examples of loss function are mean squared error for regression, cross-entropy loss for classification. Please watch this animation, which serves as a simple example to illustrate the concept of a loss function. In this scenario, the neural network is given 3 images of cat. It correctly identifies 2 but misclassifies 1. The loss function quantifies this error. Ideally, the true output should be 3, matching the number of input images, but the model's prediction is only 2. This discrepancy represents the loss. Backpropagation is an algorithm to reduce the difference between the model's predicted output and the actual output by adjusting or updating the weights and biases in the network. It works by computing the gradients, also called as partial derivatives of the loss, with respect to each weight and propagating these gradients backward through the network, layer by layer, using the chain rule. It consists of 2 major steps, including forward pass and backward pass. In forward pass, the input data flows through the network to compute predictions and loss. Watch this animation, which illustrates the forward pass in a neural network. The network processes 3 cat images, correctly identifying 2 while misclassifying 1. This demonstrates that the forward pass can sometimes lead to errors. To reduce these mistakes, the backward pass is applied, an essential technique for improving a deep learning model's performance. The backward pass starts at the output layer and moves backward, applies the chain rule to calculate gradients efficiently, and early layers receive gradients as a product of many intermediate derivatives. The objective is to minimize the loss function. As shown in this animation, after adjusting weights and biases, the loss function is minimized, and the model's output is optimized. As you can see here, the model is now performing at its best, making no mistakes, unlike the errors observed during the forward pass in the previous slide. The U appended to the weights and biases in each neuron shows that they have been updated. In a deep neural network, the early layers are the first few layers closest to the input. These layers extract basic features from raw data, for example, edges in images, simple patterns in text. However, they often suffer from the vanishing gradient problem, making learning difficult in deeper networks. The layers that are close to the output layer are said as later layers. That wraps up today's video. I hope you now have a good understanding of the concepts of loss function, backpropagation, and early versus later layers. If you found this helpful, don't forget to subscribe, like, share, and comment to stay updated with this series.